Hi again, guys. So here is another sample problem, and this is going to be with collisions. So a collision is any time that two objects hit each other. And as we know from talk about Newton's laws, when two things contact each other, we call that a force. They're pushing on each other. So you can have two things run into each other, or one thing sitting still and another run into it, or you can just have two things resting on top of each other, but either way they're in contact, there's a force. So we're going to talk about simple collision first. So I have a single object moving along at some velocity, so we'll call it M1 and V1, and it's going to hit a second object, M2, that's staying still. Well, here's the before, and we want to know about the after. Alright, so in physics and science, we're always worried about making predictions. So I have some object. It's a car hitting another car. It's a baseball hitting another baseball. It's a pool ball hitting another pool ball. Doesn't matter. We have an object moving towards another one. They're going to collide. What happens? Well, the answer, I'm sure you guessed, is it depends. Well, how massive is this object? How massive is that object? How fast is it going? If this was a pool ball going really, really, really quickly, it might hit this one, stop dead, and this one would take off. If it was a big truck, like an 18-wheeler that ran to the back of a Prius, both of them would keep moving. So there's different types of collisions, but they're all governed by the laws of physics. And one law in particular is the law of conservation of momentum. So regardless of what happens, we know that the total momentum beforehand has to be the same as the total momentum afterwards. Now, we don't know what's going to happen over here, so for the time being, let's just say that you have M1 moving at some velocity, it's called V1A for after, and M2 also moving at some velocity, V2A. Now, those velocities could be zero, in which case it would be stopped, but either way we have a way to talk about it. Since the law of conservation of momentum applies, we know the total momentum before and the total momentum after are the same. Well, we can figure out the momentum on both sides because it's just the momentum of object 1 and the momentum of object 2 added together. Same thing over here. Momentum of object 1 plus the momentum of object 2. So while momentum is not a really complicated concept, it's not a hard formula. The momentum for the object 1 is M1 times V1 plus the momentum for object 2, M2 times V2 equals total momentum. On this side, if we keep going, the momentum of object 1 is M1 times V1A plus M2 times V2A. Now, because we know that the total on both sides are the same, and the total is just adding up each individual, I can just connect this long equal sign here. Boom. Total momentum equals total momentum. Now, since M2 wasn't moving, we already know that this part is 0. So what we have is M1 times V1 before equals M1 times V1 after plus M2 times V2 after. Now, we have an issue here because there are infinite solutions to this problem. Let's say I told you a 100-kilogram object was traveling at 10 meters per second and it hit another 100-kilogram object. What would happen? Well, I put 100 here, 100 there, 100 there. So they all go away. They would all drop out. So now I have V1 equals V1 plus V2. And V1's a number. What did you say? 10 meters per second. 10 equals V1 plus V2. Well, there's an infinite combination of V1s and V2s that would solve that problem. That doesn't really help us now. However, there's not really an infinite number of things that would happen in this situation. If you saw an 18-wheeler coming in and hit a Toyota Prius, you wouldn't expect for the truck, the 18-wheeler, to bounce backwards and the Prius to go forwards. You would expect that the truck would come in, hit the Prius, and the truck would slow down a little bit, and the Prius would kind of get pushed along with it. That's what would happen. So although the law of conservation of momentum applies here, it doesn't tell the whole story. There's another part. There's also a law that says energy must be conserved, the law of conservation of energy. So not only does total momentum have to be the same, but total energy needs to be the same. Well, that E has too many pieces. There we go. So we've already talked about there being different forms of energy. There's potential energy, there's kinetic energy, and then there's also work. So if these were cars, I have a little bit of a problem. I couldn't just say, well, kinetic energy beforehand has to equal kinetic energy afterwards. Because that's not necessarily the case. If that 18-wheeler hit the Prius, sure, it would get the Prius to start moving, but it would also smash the Prius up quite a bit. If I asked you to go outside with a hammer and take a Prius that's this big and make it this big, it would take a lot of your energy. You would do a lot of work. Well, that work isn't lost, but it is accounted for. So if ahead of time the truck only has kinetic energy, but afterward the truck is moving, the Prius is moving, and some work has been done, that has to also be taken into account. Now, sometimes we don't have to worry about this. In the case of billiard balls, for instance, they don't get smashed up. They kind of bounce off each other really nicely. So we have two types of collisions, and then everything in between. You have an elastic collision and an inelastic collision. If you think of elastics, you think of superballs, and superballs bounce very well. In a perfectly elastic collision, perfectly elastic, kinetic energy is conserved. There is no work. There is no potential energy. All kinetic energy turns into all kinetic energy. For an inelastic collision, that's not the case. So, you might have all kinetic energy up front, but then you might get some work done. Now, I know I didn't put numbers in here, but this is a pretty good overview of how these collision problems work. And I'll put this one last part up here so you have it as a record. Elastic means kinetic energy before equals kinetic energy after. Inelastic means total energy is equal to total energy after. We'll practice these a little bit more, but try one. There's a problem in the unit about an asteroid hitting Earth, which has happened before. It will happen again. That's a collision problem, and this applies. So good luck, and hopefully this helped. Bye now.